Okay, I think we are ready to start, Shoham.
Yep.
So it's a great pleasure to have Shoham Letzter to give us a talk at our seminar today. She'll talk about monochromatic triangle packings, and Shoham just joined UCL as a lecturer, I believe. Congratulations on that. Okay, so please go ahead. And as normal, we will, if you have questions during the talk, please write it in the chat. I'll try to raise them to Shoham if it's something urgent. Otherwise, everything will be at the end of the talk. And we will also have an informative discussion which won't be recorded if you have questions which you don't want to be recorded.
Okay, so thank you for having me, and thank you, Liana, for getting up so early to introduce me. So I'll be talking about monochromatic triangle packings, as Liana said, and this is joint work with Vytautas Gruslys. Okay, so, and yeah, I don't know if I will be able to see the chat, but if there are any questions, I'm happy to answer. Okay, so, yeah. So let's start with the following kind of natural question about monochromatic triangles and colored graphs. So here the question is, given a red-blue coloring of Kn, what is the smallest number of monochromatic triangles I can have? And this was answered precisely by Goodman in 59. I won't give you the exact answer, but it works out to be roughly n cubed over 24. And for example, when n is even, this is an extremal example. So you partition your set into your vertices into two sets of equal size, each of size, two sets of equal size. Between them, you put blue edges, inside you put red edges, and so you can see the blue edges don't contribute anything, and the red edges contribute roughly n cubed over 24 triangles. Okay, so what we're really interested in this talk is a variant of this question. Instead of looking for a large number of monochromatic triangles, I want a large collection of pairwise edge-disjoint triangles. So precisely, I want to ask how many pairwise edge-disjoint monochromatic triangles am I guaranteed to find in any red-blue Kn? And the conjecture of Erdős, or Erdős with Fodry and Ordman, says that there should always be at least about n squared over 12 such triangles. And this, if true, would again be tied by the following, by the kind of example that we had previously as well. So, and can be even or odd. I partitioned the vertices into roughly equal sets, put red within, blue between, and you can see again the blue edges don't contribute anything, and the red edges, if you count how many they're roughly n squared over 4. So if we have edge-disjoint red triangles, we will have at most n squared over 12. Okay, so this is the conjecture, and now the first progress on this conjecture was made by Erdős, Fodry, Gould, Jacobson, and Lehel, and they showed that one can always find a collection of 3n squared over 55, roughly, edge-disjoint monochromatic triangles. And the kind of big picture idea is pretty simple. They looked at the question for n equals 11 and solved it precisely by hand, by looking at doing some kind of case analysis. And using that, they showed that in every red-blue K11, there are at least 6 edge-disjoint monochromatic triangles. And then they used this well-known result of Wilson that Kn can be decomposed or almost decomposed into copies of K11, meaning that there is a collection of edge-disjoint K11s that that covers almost all of the edges of Kn. Now you can put these two things together. So you start off with some red-blue Kn. You partition its edges into K11 each. So we have this many copies and choose 2 over 11 choose 2, roughly K11s. Each of them gives you 6 triangles, and in total you get this 3n squared over 55. Okay, so this is the first progress on this problem. And
Shoham, there was a question.
Yeah.
Lior, he asked whether, he asked whether it's the only example, the one you have for n squared over 12. He was asking it's the only typed example.
Well, so the conjecture was only asymptotic. It said n squared over 12 plus little over n squared. So
I think he just the upper term, whether it's the only one, the only known.
So we'll see. Sorry, I mean, yeah. So for the n squared over 12, like you can just perturb the example a little bit, and you'll still get an n squared over 12 asymptotically. But also you can. We'll see in a bit, like you can slightly change it, and there's also some parity issue. So when you're talking about decompositions, then there might be parity issues. So maybe something slightly different is actually better. Yeah, depending on the parity, actually, I was looking at it, just thinking about the exact thing, and then it might actually be beneficial to move one vertex from one side to the other. But yeah, there isn't, like the conjecture doesn't specify exactly what the extremal thing is, but just roughly speaking that it should look bipartite. But I'll say a bit more later. Okay, so having seen this, on the one hand, like maybe you see this result and you want to improve it. So an obvious kind of thing to do is to try to look at k and 0 for larger and 0, solve the problem there, and then you should automatically get an improvement for large n by just the same idea. However, no matter how large an n0 you take, you will never be able to get quite to this 1 over 12. You'll have an error time of order 1 over n0. And more problematic issue is that even this K11 was quite hard to calculate precisely. So pushing it a lot further looks somewhat intractable. Okay. Then here's, I guess, the next progress on this problem. Kivash and Sudakov, they actually proved something pretty close to this n squared over 12. They proved n squared over 12 plus 12.89. And one thing they did is they reduced the problem, which is about, I guess, finding edge-disjoint triangles to a fractional version of this using this result of Haxel and Rodel that I'll mention a bit later. And this enabled them to use computers. So for K11, you can do things by hand, but it gets kind of nasty, and later it gets pretty much intractable. So at least you can do a bit better by using the fractional version and using computer. And they had a kind of nicer averaging trick that allowed them to push this bound for 11 to get a better bound than what we would have gotten by just doing Wilson's, using Wilson's theorem. Okay, however, even with this better trick, just looking at a small n0 will not prove the result, no matter how large my n0 is. So you'll have, instead of this 1 over n0 error term, you now will have a 1 over n0 squared error term. So again, you can hope to improve, but it both gets intractable and it will never prove this 1 over 12 precisely. So okay, so this problem seemed like maybe it's not so easy, and therefore Alon and Daniel suggested to look at an easier version. So what if we assume that one of the colors is triangle free? which is kind of reasonable because the example that we looked at, in the example that we looked at, the blue color was triangle free. And so if we force the blue graph to be triangle free, the answer should be the same. So the question is, yeah, so the answer should be the same. And so this works out to be this kind of asymmetric version of Erdős's conjecture, given a graph G on n vertices whose complement is triangle free. Can we find n squared over 12 edge disjoint triangles? Okay, so this is kind of weakening of the original conjecture where the blue edges are triangle free and so they cannot participate in this monochromatic triangle packing. So yeah, we're only interested in the red graph, which we call G now. And there was some work on this done by Letzter, and he showed that the answer is yes, I can find roughly n squared over 12 edge disjoint triangles in G if either the number of edges is quite close to the extremal number. In the extremal example, the number would be roughly n squared over 4, so this is quite close to it, or if the number of edges is quite far from the extremal number. And recently, Misha proved this or answered this alone and linear question affirmatively. And moreover, he proved a stability version of the result, meaning either G complement is close to being bipartite. So our example kind of looks like the example that we had, or G has significantly more than n squared over 12 edge disjoint triangles. Okay, and our contribution is firstly to solve Erdős's conjecture. So we show that in every red, blue Kn, we can find n squared over 12 edge disjoint monochromatic triangles. And moreover, like Misha, we prove a stability version of this result. So we prove that in every such coloring, either one of the colors is close to bipartite, or there are significantly more than n squared over 12 edge disjoint monochromatic triangles. So this kind of partially answers what Lior was asking. I mean, maybe there are various examples, but they all should look like this complete bipartite example. Okay, so yeah, so I want to talk about mostly the proof of the first result. But first, like Misha and like Kivash and Sudakov before us, we are going to look at a fractional version of this problem. So I should start by talking about fractional triangle packings. Okay, so a fractional triangle packing in a graph G is a function that assigns a weight between 0, 1 to each of the triangles in G. And it does it in such a way that every edge, the weight at every edge, which we define to be the sum of the weights of the triangles containing the edge, is at most 1. So a quick sanity check: if instead of giving weights in the interval 0, 1, we gave weights either 0 or 1, then the triangles that receive the weight 1 have to be edge disjoint, because otherwise there would be an edge with weights at least 2. Okay, so this is just a kind of usual way of getting a fractional relaxation of an integer problem. And here is an example. So I have this 5-wheel, and I give each of the triangles in the 5-wheel weight 1/2, and I can see that these edges that join the central vertex have weight 1, and the outer edges have weight 1/2. So indeed, this is a fractional triangle packing. And the parameter of interest is this fractional triangle packing number, which I will call in short packing number. So this is the maximum over 3 times the sum of the weights of the triangles over all fractional triangle packings. Or equivalently, this is the maximum of the sum of the weights of the edges over all fractional triangle packings. So a few remarks here. Usually this mu is used to denote the kind of integer version, so just the packing number, not the fractional packing number. And the fractional is denoted by a star here, but just for convenience, I use this notation. And also normally we don't have this extra 3, but it's just, for us, it's more convenient to think of the weight of the edges that are covered rather than the weights of the triangles. So we prefer this scale where we can think of how many edges are covered, essentially. Okay, and now just to see an example, you can try to convince yourself that this fractional, this packing that I gave here of this 5-wheel is best possible, gives the largest sum of weights of triangles, and the exact number works out to be 3 for this 3 times 5 because there are 5 triangles times 1/2 because each triangle has weight 1/2. And another easy example, if we look at a complete graph on n vertices and n is not 2, then I can cover fully all of the edges by giving each triangle the same weight, the same suitable weight. Okay, so this was the fractional version of a collection of edge-disjoint triangles, but I want to look at the monochromatic variant of this. So a monochromatic fractional triangle packing in a red-blue graph G is just a fractional triangle packing omega where where triangles that are not monochromatic receive weight 0. Or in other words, I'm only allowed to give non-zero weight to monochromatic triangles. Okay, and then I have the same kind of definition. The monochromatic fractional triangle packing number or monochromatic packing number is this new subscript mono of G, is the maximum of 3 times the sum of the weights of the triangles over all monochromatic fractional triangle packing. And equivalently, this is just the packing number of the red graph plus the packing number of the blue graph. Okay, and as an example, I have my standard example of a red-blue graph in this talk. And here, again, blue edges do not contribute. And we know that the packing number of a complete graph is just the number of edges, unless the number of vertices is tiny. And so the packing number of this thing is the packing number, is the number of edges here plus the number of edges here, which works out to be n minus 1 squared over 4 rounded down, or roughly speaking, n squared minus 2n. And you can do a slight variation on this. You can add some matching between the two sets. And this wouldn't change anything because these edges do not participate in any monochromatic triangle. Okay, so these were some definitions, and now given these definitions, there is the obvious or natural extremal question, well, how small can the monochromatic fractional triangle packing number be among red-blue complete graphs? And we answer this question as follows. So whenever G is a red-blue Kn and n is not too small, then the packing number is always at least this n minus 1 squared over 4 rounded down. And here we characterize all the extremal examples, so they all look like this. Our usual example plus a matching. So maybe in the integer version, you may have to do some variations, but here the examples are just this. So yeah, okay, so just a remark, I do need to take n not tiny here because of this pentagon blow up. So pentagon blow up is a graph, or red-blue complete graph, whose vertices can be partitioned into 5 blobs, 5, let's say, non-empty blobs, such that the edges, the red edges between the blobs form a blow up of a C5. So here is the red blow up of a C5. And the blue edges between the blobs also form a blow up of a C5 like this. And inside I can do whatever I want. Okay, so this is a pentagon blow up. And now if I look at the specific pentagon blow up where the blobs have size 3, I claim this is the packing number. And this comes from noticing that every monochromatic triangle has to have at least one edge in a blob. And actually it turns out that you can cover all of the edges in the blobs with triangles that have exactly one edge in the blob, and then it will work out, the packing number will work out to be the number of edges inside, which is 5 times 3 times 3, because we have the scaling. And the point of this was that this is lower than the bound that we claimed in the theorem. Okay, so this shows that the theorem does not hold for n equals 15. Okay, and why is it even relevant to talk about fractional triangle packings? Well, Haxel and Rodel proved more generally, just not just for triangles, but for any kind of H packing. But here, let's just think about triangles. They proved that the actual packing number, which is just the maximum number of edge-disjoint triangles, equals the fractional packing number, which is what we have here. And using this, we get conjecture. We get that since here we know that we have fractional packing that covers roughly n squared over 4 edges, the same holds for the integer version, and that works out to be n squared over 12 edge-disjoint monochromatic triangles. Okay, so now I want to start talking about, or starting to head towards the proof. And the first thing that you might want to do is this averaging idea. So here, this is how it goes. We start with the red, blue, k, and plus 1, g. And then for every vertex in g, I look at g minus u. So this would be a red, blue, kn. And I take omega sub u to be the largest monochromatic fractional triangle packing in this smaller graph. And then I put them all together. So I look at the sum of all these omega sub u's and divide by n minus 1. So this is not quite the average because I have n plus 1 guys here, and I divide by n minus 1, almost. And the point of this is that omega turns out to be a monochromatic fractional triangle packing in G. And why is that? If I take an edge xy, then note that xy does not play a role, does not appear in G minus x or in G minus y. So in omega sub x and omega sub y, the edge xy receives weight 0. And so it receives non-zero weight from at most n minus 1 packings omega sub u, which altogether gives an upper bound of 1. Okay, so we showed that every edge receives weight at most 1 under omega, which tells us that omega is indeed a triangle packing, fractional triangle packing. Okay, and using this, we get to the following proposition. So suppose that the packing number of G minus U is larger than alpha times n minus 1 for every vertex U. Then the packing number of G itself is at least this scaled average, which works out to be larger than alpha times n plus 1. So the point is, it turns out that it's convenient to use the scaling alpha times n minus 1 because then it just kind of gives seems kind of suggestive towards an inductive idea. Okay, so this proposition kind of tells us that we better look at things that look like this, some constant times n minus 1. However, our aim was to show a lower bound of something like n minus 1 squared over 4, which is not quite of that form. So it might be a good idea to try to characterize things that are whose packing number lies below n times n minus 1 over 4. And this is indeed what we do here. So again, if G is a red blue KN with n not too small, and its packing number is at most n times n minus 1 over 4, then we claim that one of the colors is n over 8 close to bipartite, which means that I can remove up to n over 8 edges and make one of the colors bipartite. Okay, so let's see where this n over 8 comes from. So let's look at our favorite example and just plant up to n over 8 blue edges in these red parts. And it should be easy to see that I can cover these blue edges by these disjoint cross blue triangles. And now if I look at any packing omega, I can notice that the weight of the cross edges is at most n over 4, because every triangle that contains any cross edges contains at least one of these blue edges. There are at most n over 8 of them, so the weight of the cross edges is at most twice that, because in every triangle there can be at most 2 cross edges. Trivially, the weight of the edges in the parts is the number of edges in the parts, which is about n squared minus 2n over 4. And summing these two things together, we get our promised n times n minus 1 over 4. So this shows you that n over 8, I mean, if you look at this example with n over 8, then you're still within the allowed bound. And actually, if you go up a bit, you can do a similar argument to see that you'll get above n times n minus 1 over 4. And again, we have the same enemy, the pentagon blob, which tells me that this is not true for smaller n. So for n equals 25, the pentagon blow up, the balanced pentagon blow up gives me this this expression, but it is not at all close to, neither of the colors is close to bipartite. Okay, so my plan is to give you an idea of how to prove this. And then remember that really our aim was to prove this extremal result, but I will not say much about it. Just once you have this, you can, with some effort, get this extremal result. Okay. So we mentioned this averaging trick, and indeed this is what I'm going to use. So I'm going to do induction, and this is how the induction step is going to look like. So I'm starting with a red-blue k plus 1 graph G, whose packing number is below this n times n plus 1 over 4. So here's my G. And now I know by this averaging proposition that for at least one vertex, if I remove it, I get packing number at most n times n minus 1 over 4. Okay, so say this is this graph that I get after removing U. And then by induction, I can assume that the blue edges in this H and this new graph form a graph that is close to being bipartite, that is n over 8 close to bipartite. This means that there is some bipartition of the vertices such that there are at most n over 8 blue edges in either part. And our aim is to show that the blue graph in G is close to bipartite. Okay, so this is my plan, and now let's see how I'm going to try to achieve it. Sorry, one definition. So I'm going to be interested in these neighborhoods of U. So the red neighborhood of U in X1 is R1, in X2 is R2, and similarly B1 and B2 are the blue neighborhoods of U in X1 and X2. Very good. So my first aim is to show that in H, I can cover the blue edges in the parts by disjoint cross triangles. Okay, so this is what I mean. I have my blue edges in the parts, and I'm trying to find a collection of cross triangles, so triangles that have one vertex in one side and two in the other. I'm trying to cover all the edges. But suppose that I tried my best and I did not manage to cover everything. So I have one edge that is left uncovered. Now, because we have only n/8 such edges, we will have some vertices that are kind of free for this guy. And these vertices cannot have two blue neighbors to this edge, because then we would get a bigger pattern here. So together, the two vertices have a large red neighborhood. Now, if I look at these red neighborhoods, since X2 has few blue edges, then these guys should have large red matchings. And then altogether, this gives me quite a few edge-disjoint monochromatic cross triangles. Now, let's look at the red graphs in X1 and X2 minus maybe these edges that I used for these cross triangles. So these guys are almost complete, like they're missing some linear number of edges. And so I claim that they can be decomposed, well, can be fractionally decomposed into triangles, meaning that there is a fractional triangle packing that covers all the remaining red edges. And then you do a calculation and you find that there is a packing in H that covers too many edges, which is a contradiction to what we assumed in H. We assume that it has packing number at most distinct. Okay, so just to summarize, I now showed that these blue edges in X1 and X2 can be covered by disjoint blue cross triangles. Okay, now my next aim, and soon I will show you how I can put them together. So my next aim is to look at these blue neighborhoods, B1 and B2, and I claim that there is a matching that covers one of them. Say B1 is the small one, then I claim that there is a matching that covers B1. Okay, so let's take a maximum matching and suppose that it does not cover B1. Then I have all these many red edges between the remainder in B1 and remainder in B2, because otherwise we could get a bigger matching. Now, again, because X1 and X2 are sparse, I can find a biggish red matching here and biggish red matching here. So I put them together. And in total, this gives me quite a few monochromatic cross triangles. And moreover, again, this bit is sparse and this bit is sparse, so they will both have largish red matchings. And so putting this together with U, we find that there are many disjoint monochromatic triangles that contain U. I think somebody is unmuted.
In the early days for exceptional players in a variant or in a couple of chess variants.
Somebody is unmuted. Can you please try to mute yourself?
And they don't give it anymore.
Yes,
yeah, it Chess Master.
Oh, okay, thank you.
White Dancing Rockstar. And they don't give it out anymore, but there's still a couple of LMs around. For example, Jan Lee for his contribution to the Crazy House.
Okay, I think we're good.
Okay, thank you. Yeah, so we have many disjoint monochromatic cross triangles. We have many triangles that contain U. and somehow putting these two things together. Oh, sorry. And again, as before, what remains in X1 and X2 is almost complete, so it has a triangle decomposition. Putting the two things together, or three things together, I guess, we get a packing in G this time that is, again, too large. Okay, so now I know that there is a perfect matching here, and I know that I can cover all these blue edges. So now I'm going to put U in X1. So you can kind of think of U as belonging to the left-hand side. Now I know that there is a matching that covers B1. I also know that these blue edges in the two sides can be covered by disjoint blue cross triangles. And so now you can imagine, since U is in the left-hand side, then essentially what this means is that in this new bipartition, I managed to cover all the blue edges by disjoint cross blue triangles. Now, again, so far I only touched blue guys, so I can look at what remains in red here and what remains in red here. Again, it's almost complete, so it can be decomposed. And then you have this calculation similarly to what we did with the extremal example, and it will turn out that if I have too many blue edges in either in total in X1 prime and X2, then I will get a too large packing number. Okay, so this tells me that I can put U in X1 and obtain the bipartition that I wanted that has few blue triangles in the parts. So this essentially completes our induction step with the exception of one point. I kept saying a graph is almost complete, so it has a triangle decomposition. Well, here is a precise statement that we use. Suppose that I have a graph on n vertices with this many edges, so it has at most n-4 missing edges, and it's not too small, I guess. Then F, with these conditions, so F is kind of almost complete. With these conditions, F has a fractional triangle decomposition. Okay, so this n-4 is again tight. Here's an example on 7 vertices. I take one vertex, put all the missing edges incident with it, and one extra missing edge. And now if I look at this edge, it is in exactly one triangle in F, this triangle. And so if I want to cover this edge completely, I need to give this triangle weight 1. But then this edge will not have any triangles that it can join to, so I cannot cover all of the edges in this F. Okay, so yeah, we proved this thing, but the proof ended up being really quite annoyingly tricky. Used again induction, and we had to strengthen it a bit to account for slightly more missing edges, and also it was convenient for us to look at packings where all the triangles have weight at most 1/2. And our induction base was by computer search. Yeah, so beginning when we kind of had this statement in mind, and we tried to find a proof, and we really didn't expect it to be so difficult. And what's also a bit annoying about this is that if you're allowed to take n large enough, then this would follow quite easily from existing results about fractional triangle decompositions in graphs with large minimum degree. So somehow we really needed to prove this because we really need n to be quite small, but for larger n, this should be provable using existing tools. Okay, so now with this thing in hand and with this induction step that we did, we managed to prove an induction step, but of course we need the induction base as well. In other words, we need to prove this statement for some n0. We need to prove that if G is a red blue Kn with packing number at most n times n-1/4, then one of the colors is n/8 close to bipartite. So ideally, if you recall, this statement is false for n equals 25. So ideally, we would prove it for n equals 26. However, our approach was to use computer search, and 26 turns out to be a bit too large for, at least with our methods. So instead, we did a computer search up to n equals 17. And we proved that if the packing number is small, then either what we expect happens, one of the colors is close to bipartite, or the other thing that I guess one would expect happens, our graph is close to being a pentagon blowup. And then we kind of can use induction on these graphs, and we handle the pentagons separately. Okay, so this is our proof. Now let me say a little bit more about the computer search. So firstly, the kind of general idea of calculating packing numbers is by the so-called linear programming, which is just a general name for optimization problems where everything is linear. So we're trying to optimize some linear function, and there are some linear constraints. And there are algorithms for this that are efficient in practice, even though in theory not quite polynomial. So this is what we use just to calculate the packing number of some graph. Okay, now here's again this averaging comes up. Given red, blue, kn with small packing number, if I repeat this averaging n times, then I will find the sequence G1 up to Gn, such that Gi is an induced graph on I vertices, and it has small packing number. Okay, so using this gives the following kind of plan for finding all the possible G's. So given a list Li of all possible red, blue, Ki's with small packing number, to find the same list for one larger, for I plus 1, I just need to calculate the packing number for every example which is formed by taking something from this list and extending it by one vertex. However, this is gets a bit slow, I guess, when you, I don't know, when you look at n equals 20 and you have one example, then the total number of ways of extending it is 2 to the 20, so that's already quite a lot. So one way to speed things up a little bit in our algorithm is to expose the edges to the new vertex one by one. So we again look at all the examples in Li, and instead of looking immediately at all the edges from the new vertex to this example, I look one by one. I give each edge some color. And the advantage is that sometimes examples can be ruled out before I exposed all of the edges. So this gives us some bit of speed up. And the other advantage of this, so in any given moment when I'm calculating the packing number, I'm calculating the packing number of some graph that I already analyzed plus an extra edge. And it turns out that when I'm calculating the packing number of this new thing, it's convenient to start with the maximum packing in F and kind of modify it. Instead of the more naive thing to do is just to start with weight 0 and calculate the packing number. Okay, so this was a little bit about computer search. Now, I think I can say a bit about the stability, and then I will finish. Okay, so what's the setup here? I'm starting with the red, blue, Kn called G, and I assume that the red and blue graphs are both far from being bipartite. So in other words, this example G is far from our extremal example. And my goal is to show that the number of, that I can find a collection of edge-disjoint monochromatic triangles with significantly more than n squared over 12 edges, triangles. Okay, so the idea is to use this result of Alon, Shapira, and Sudakov, and this is already an idea that we're borrowing from Misha Tjomkin's paper. So what they proved in particular implies that if I look at a random induced subgraph of these graphs, the red graph and the blue graph, on a large but constant number of vertices, then I will get with high probability something that is again quite far from being bipartite. So again, if I sample from this G, if I sample some smallish number of vertices, then since both the red and the blue graph are far from bipartite, then this thing that I sampled, both red and blue graphs will again be far from bipartite. Now I'm going to use this averaging trick again. So just iterating it, I will get that the packing number of G is at most this 1 over n minus 2 choose n minus 2 times the sum of all packing numbers of the induced graph on m vertices. Now I always have, this is the first result that I mentioned about fractional packing numbers. I always have this lower bound m times n minus 2 over 4. And then when things are quite far from bipartite, I have that the packing number is a bit above this m times n minus 1 over 4. So what I showed you was essentially without this eta when eta is 0. And we kind of leveraged that result plus similar arguments to get this kind of stability version of it. Okay, so I get that all the induced guys are quite large, and almost all of them have even larger packing number, and putting them together will work out to show that packing number of G is significantly above this quarter times n squared. And again, using Haxel-Rodel, it shows that in the integer world in G, there is a collection of significantly more than n squared over 12 disjoint monochromatic triangles. Okay, so this was all I wanted to tell about our results, and now I'll just finish with a few open problems. So one obvious thing is what is the exact number of edge-disjoint monochromatic triangles that I'm guaranteed to find in every red blue KN? So as I said at the beginning here, there is some issue with parity. So sometimes it's better, instead of to take, say, n over 2 and n over 2, to take n over 2 minus 1 and n over 2 plus 1, because that increases the number of edges in the parts by only a little bit, but maybe if you have some parity issue, then you can gain somewhat because of that. But okay, so I would expect this to be kind of doable using our stability result, and I would expect the answer to essentially be complete bipartite, but maybe not quite balanced, just almost balanced. But I don't know exactly. Okay, now another maybe obvious but a bit harder question most likely is to generalize this, instead of triangles, to look at copies of H, and instead of 2 colors to look at R colors. So how many edge-disjoint monochromatic copies of H am I guaranteed to find in every R-colored KN? Yeah, so this I would expect to be hard, but maybe, I don't know, maybe it's not completely impossible for triangles with more colors or something. Yeah, and the last kind of question that is similar but a bit different flavor is a conjecture of Jacobson. It says that, well, he conjectured that in every red blue KN, there is a collection of n squared over 20 edge-disjoint monochromatic triangles of the same color. So if you think about our result, we showed that in total there are n squared over 12. So at least n squared over 24 of them should have the same color. However, we also show that if we have close to n squared over 12, then we should be, one of the colors is close to bipartite, in which case there would be way more than this many edge-disjoint monochromatic triangles. So I guess our result kind of tells me that I can do somewhat better than n squared over 24, but yeah, but the conjecture is n squared over 20, and that should be tight. Well, that is tight for the balanced pentagon blowups that we have seen. Okay, so that's all. Thank you.
Thank you very much, Shoham, for a wonderful talk. Before the questions, I ask everyone to unmute themselves, and let's give a round of applause to Shoham. Okay, now just to have some order, if you have questions, could you please write it in the chat, and we will have some order who asks the questions first. Okay.
Yeah, so Lior is asking for KR and two colors. Is the conjecture that the extremal example is the Turan graph? I would guess so. I haven't really thought about it, but that kind of seems like the idea. I'm not sure.
Any more questions?
Like, I guess the problem for KR, I mean, for triangles, the kind of enemy was the pentagon blowup, which is the kind of Ramsey graph for triangles. But then for KR, you may need to know what the Ramsey, what the worst kind of coloring is for KR, and that's sort of not really known, so that might be a problem.
David Conlon says,
yeah, computational aspect is a problem. I was thinking when we were proving this, so we had this induction base, and I was hoping to somehow avoid the induction step, because the induction step is kind of annoying. You have to make sure that it works for very small n. So I was hoping to at least have an idea of leveraging from something about small n to something about larger n. But even that I couldn't figure out how to do. So it would be, I guess, problematic to solve anything better. But yeah, I don't know. Yeah, so Misha is asking our n/8 theorem. Is it what you conjectured? I think it's exactly what you conjectured. Yeah, I think you literally conjectured what I just stated here. So it should be true. And he's also asking how complicated is the proof? Is there a lot of case analysis since one has to do it exactly for small n? So, okay, there is obviously a lot of case analysis, but most of it is dealt with by the computer, who is better at dealing with case analysis than we are. What did I want to say? But then you still have this annoying thing that that the computer doesn't quite push beyond this pentagon. So we do the pentagons on our own, which is somewhat, that's probably the most kind of case analysis part. The rest is not so much, the problem is not so much case analysis for the induction step, but just the fact that you really need to take very exact bounds to be sure that you get a precise n/8 and not slightly below, because your n is not large. So that's the main complication. Yoshi asks if there is a manuscript. There is. I guess the main bottleneck currently is one of my co-authors who has to approve it, but hopefully, I mean, it is pretty much finished, so I guess we'll try to upload something very soon. Oh, Misha is asking Okay, for the induction step, it's not so much case analysis, but you have to be just careful with everything that you're doing. So you need, I agree, you need some bounds on the parts, which is what we do first. I didn't mention that. And then essentially you follow the steps. So it's not really case analysis, but just some annoying calculations.
Any more questions? Okay, well, if not, let's give another round of applause to Shoham, and then we'll have the informative session where things won't be recorded. So if you want to stay for that, okay?
Thank you. Yeah.